This week's multiple choice Monday is looking at Kp and gaseous equilibrium. So while we try and explain some of this, let's think about first of all what the P in Kp means. It actually stands for partial pressure, not just the total pressure. And we should remember from our calculations that partial pressure is equal to the mole fraction, so the moles of any particular gas divided by the total number of moles, and then that's times by total pressure. So partial pressure is just basically how much of the total pressure each of the gases is exerting, and that's directly proportional to moles because we know about our PV equals nRT, that pressure is therefore proportional to n number of moles. Okay, so what we have to try and work out here is what we should know in terms of an equilibrium and pressure changes is that if we increase the total pressure, when we say pressure, we mean total pressure, then that means that the equilibrium will shift towards the side with fewer moles of gas. And it is important to say of gas here because there could be equilibrium, for example, that involves solids and gases, and it's only the gases that contribute to pressure. So that's a sort of descriptive thing related to Le Chatelier's principle. If we have fewer moles of gas, the overall pressure will come down. Okay, so let's have a look at what will happen in terms of all of the different things that are here. So the value of Kp increases cannot be true, and that is because we have not changed temperature. So you've got to remember that Kp, Kc only change with temperature. We are going to explain how the equilibrium position changes without changing the value of Kp. Because the equilibrium position does definitely change. There are 2 moles of gas on the right hand side and 4 on the left. So it's going to shift to the right hand side, which means we're going to make more ammonia and we're going to use up more of the nitrogen and hydrogen. Now, if we're doing this, if we're saying that we're shifting so that more nitrogen and hydrogen react to produce more ammonia, that means we're reducing the amount of stuff on the left hand side, which is equal to 4 moles of gas, and we're replacing it essentially with ammonia, which is equal to 2 moles of gas. So actually no, if we increase the pressure, the total number of moles of gas in the mixture is actually going to decrease. So it's not going to increase. Well, that's really weird, because why would it do that? A lot of the times, some of the ways that we get confused with equilibrium is we sometimes assume that like the number of moles has to stay the same, and that's never the choice. So we've decided that they're all wrong, and therefore the mole fraction of ammonia increases. Well, yeah, because we know if it shifts to the right hand side, there are more moles of NH3 than there were before, and if there are more moles, no matter what's happened to the total moles, the mole fraction will have increased. Okay, let's have a look at the maths and see if we can work this out. So Kp is equal to the partial pressure of NH3 squared. So I'm going to say Mf is my mole fraction, and I'm going to call P my total pressure. And all of that is squared. I should probably write that that is for ammonia as well. So it is, P stays the same. So let's write it slightly more obviously. NH3 times P, and the whole thing is squared. Underneath we have the mole fraction of N2 times P, that's not squared, and we're also going to times that by the mole fraction of H2 times P, and that is cubed. Okay, so we've said that Kp must be constant. What we're doing when we change total pressure, when we increase it, is we are increasing the value of P. But if you now look at this equation, you can see that on the top we have P squared, and on the bottom we have P to the power 4, because N2 is times by pressure, H2 is times by pressure, but then we take the partial pressure of H2 and we cube it. So it's not even what we're doing to the pressure. We're increasing it, but it's having a disproportionate effect on the bottom half of the equation because we are increasing it by, like, we're a power of 4, whereas on the top we're increasing it a power of 2. So from that, it should be kind of obvious that Kp cannot stay the same if the mole fraction stays the same. So we have to change the mole fraction of all three of those substances because they're all related to each other. So what has to happen is the mole fraction of ammonia has to increase and the mole fraction of nitrogen and hydrogen has to decrease in order for Kp to be constant, and we know that it's constant because that is our definition of Kp. So therefore the mole fraction and the number of moles of ammonia goes up and the moles of the other two goes down, but Kp stays the same. So revision materials are on my website. Go and find all the different practice questions and walkthrough videos you can do there. If you haven't signed up to my email club, Cation Club, do that as well. You get emails weekly giving you information about new videos, new resources. My A-level masterclasses are going to be covering equilibrium this week, and I've got a couple of spaces for students if they want to join live on those. You can join both classes for just £15. That's going to cover Kp, Kc and the second class acid-base equilibrium. But there's also a 50% discount until the end of May if you just want to access the recordings, which is 23 A-level classes plus predicted papers, all for about £32.50 for access till way past the end of your exams. And of course, if you subscribe to my YouTube channel, you'll get new videos every week as well.